Hi, everyone. My name is Sean Even. I'm representing the MiNiRo-Lab from University of Notre Dame. And today I'm going to be talking about a recent work that we submitted to ICER called Evaluating Tools for Collective Soil Excavation, Challenges and Insights. So let's get this going. So basically, the motivation for this is collective excavation. So you see this behavior a lot in nature with ants and other insects where they bore a tunnel together. We want to do that same thing with robots, right? So that's the goal of this paper. So this is the system that we built. It comprises of a refabricated CNC machine. You can see some soil testing, and then we added a dust cover just because these things are pretty dirty, right? So here are the three end effectors that we tested: the rototiller, which is the kind of blade digging in, the bucket, and the drill, which are more self-explanatory. So that's what you see on the left here. You'll see the moisture versus compaction and how they relate. More moisture equals more compaction, and on the right you can see how much flow rate we can get versus moisture. Um, okay, here's the drill test. The drill on the first cell, you'll see a camera point of view. Below, you're going to see live force sensor data in X, Y, Z. On the top right, you're going to see a point cloud representation of that. Middle right, you're going to see an isotropic view. You can tell that it's really dusty. And on the bottom right, you can see the trajectory that it's following. You can tell that when this is doing it, it's kicking up a ton of dust, right? You can't really see much on the point cloud front. And this is a huge challenge because if we want to use that depth camera, it's really noisy and it's hard to do. The next one is bucket. So there's kind of three phases of the bucket. We call it the penetrate phase, the drag phase, and the drop phase, right? So you can see those happening iteratively, right? It kind of gets into this 0 degree position. It flicks up, grabs the dirt, comes back and drops it. So you can tell that this is following the same kind of trajectory. We found the bucket was really good at excavating like loose soil. So this is why we wanted on the smaller elements of our swarm. And then the third was the best of the three. It was called the rototiller. Because of its relative, performance, we only had three different penetration points, but it's just going in, it's pulling out soil the whole time. And the last thing is that, we see that visualization is a huge challenge here. So if we want to make something autonomous, then we need to make a system that can basically segment the image, using AI. And we found this to be the best way to do that because you have your end effector in the field of view. So you need to know what's the soil. So the strategy that we came up with was just wanting to find the closest point to the camera and digging there, right? But we couldn't do that if we didn't segment the image to exclude the end effector because that's going to be the closest point. But also another big challenge we saw was how much the dust affected our ability to visualize the surface. And this is kind of a problem for future research. It's kind of an open problem. Is how do you register a dynamic surface when you have a very noisy reading? And this is something we are still working on trying to solve, but we still know a lot about how to, interact with soil and how to, dig through it based on our test that we conducted. Thanks for your time.